Okay, so in this video we want to have a look at the general solution of trigonometric equations. So rather than coming up with specific solutions within a specific domain, what we now want to look at is how can we express those infinitely many solutions to a trig equation in a general way. So what we've seen is, let's just have a quick look. I've got the CAS open here. I'm just going to make sure I'm in radian mode. Sorry, there we go. My Year 10 class are doing trigonometry as well, so my CAS is changing modes frequently. So let's just have a look at what happens when we solve this equation. So 3 times tan of x is equal to negative square root of 3. Okay, so, oh, sorry, solve that. Solve that for x. Okay. Alright, so my CAS gives me this. And this is not, it's not broken in any way. It's using n1, in bold, as a parameter. So x is equal to some sort of some sort of integer multiplied by pi and then subtract pi on 6. Okay, and that should enable us to generate all of the solutions. Okay, it's a general solution. Now if we were to write that down, I'm going to have a look at how we do this by hand in a second, but just quickly, if we were to write that solution down, so if this was just a CAS question, we were writing down our answer, we wouldn't write down n1 because that's the language of my specific brand of CAS. We could just write n, or you could use another parameter. T is a common letter used for a parameter, as is the Greek letter lambda. We've seen that previously. So I might just use n, but I'm not going to write n1 because if I had solved 4 other equations before this, this would say n5. It's just so that it can have a number of parameters. So we're going to say n pi minus pi on 6. So I want to be clear what this is doing. Okay, so this is having a look at, I'm going to erase this in a second, so don't copy this down, I'm just having a look at it. Then we're going to look at go back and look at how we do it by hand. So for example, when, so n is, we'd also need to add the clarification, that n must be an integer. Without that, the solution is not complete. Okay, this isn't giving you all the solutions if n is 6.4, okay? N must be an integer, so that is a positive, negative, whole number, or 0. So what we're seeing here is we've got the whole family of solutions. When n is equal to 0, x is negative pi on 6. When n equals 1, x is pi minus pi on 6, so that's 5 pi on 6. When n equals 2, x is 2 pi minus pi on 6, that's 11 pi on 6. When n equals, let's say, negative 1, x is negative pi minus pi on 6, that's minus 7 pi on 6. When n is negative 2, x is negative 2 pi minus pi on 6, that's negative 13 pi on 6. And we could go on forever. Different values of n gives me a different solution. If I look at every single integer n, I get every single solution to the equation, of which there are infinitely many. Okay, let me just erase that for a second, and let's go back to, alright, well, how do we actually get to this solution ourselves? And it's actually not as hard as it might seem, especially not for tan. It's a bit more complicated for some of the other trig functions. Okay, so find the general solution to each of the following. Initial process is still the same. We want to get the tan function on its own, and we want to think through where in the unit circle are my solutions on the basis of the exact value, whether tan is positive or negative. Sorry, that's root 3 on 3. And just so that we can think in terms of our special triangles, root 3 on 3 is the same as 1 on root 3. Okay, so that means, in terms of exact values, let's think about our special triangles. Half an equilateral triangle. We get 1 on root 3. Tan is opposite over adjacent if we are talking about pi on 6. Tan is negative in this instance, so we're looking at the second and fourth quadrants. Okay, so this, let's try that again. These are the locations of my solutions. So pi on 6 down from the x-axis in the fourth quadrant, pi on 6 up from the x-axis in the second quadrant. Now the advantage with tan is every single solution is just about plus pi plus another pi. Okay, so we actually only need to, we'll see in other for sine and cos, we're going to need to give sort of two separate families of solutions, and we'll say that when we use the cas as well. But for tan, let's just think about one solution to this is at negative pi on 6. So we know that x is equal to negative pi on 6, but equally we know that if we add pi to that, we'll get the next solution. If we add pi to that again, we'll get another solution. Add pi again, we'll get another, if we just subtract pi's. So if we add integer multiples of pi onto negative pi on 6, we'll get the full family of solutions. Now equally, we could have written this solution as x equals 5 pi on 6 plus n pi, where n is an integer. Okay, so one solution. The convention is usually, obviously if there's a first quadrant solution, we would use that one. And then it varies a bit depending on the function type. So you might then either go to the solution in the first negative solution in the fourth quadrant, or you might go around into the second quadrant. So it would also be perfectly correct to give this solution as 5 pi on 6 plus n pi, where n is an integer. Okay, it's the same solution, same family of solutions. Okay, let's have a think about the second one. Sine of 3x is equal to 1 on root 2. Okay, so 1 on root 2 comes from the special triangle with 45-degree angles in it, so the exact value we're dealing with here is pi on 4, and sine is positive. Okay, so we are looking at, in terms of locations of the solutions, pi on 4 in the first quadrant, pi on 4 in the second quadrant. Okay, and then, unlike tan, there's not the same distance between every single solution. So, if we look at the pi on 4 solution, and if we add on 2 pi, we'll get another solution. Add 2 pi, add 2 pi, add 2 pi. Similarly, if we look at the 3 pi on 4 solution and add 2 pi to that, plus 2 pi, we get that family of solutions. So you've sort of got to think about it as there being kind of two families of solutions here. So we're going to have, and also we're equal to 3x here, so we need to be a bit careful. So 3x, it could be equal to pi on 4, but then we would need to add multiples of 2 pi onto that. Or it could be equal to 3 pi on 4, which is the second quadrant solution, but we would need to add multiples of 2 pi to that. And we're talking about integer multiples, so we need to specify that n must be an integer. Okay, now we've got to deal with the 3. So we need to divide by 3. Now, let's just look at this equation in isolation. This is where people go wrong here. If you then just say, okay, well x is going to be equal to pi on 12 plus 2 pi n, your solution's not right, because you haven't divided the whole equation by 3. Dividing the whole equation by 3 would also mean that happens. And that makes sense, because actually what we're doing there is we're saying that there's a solution at pi on 2, and then if you add on 2 pi on 3, you'll get to another solution. And 2 pi on 3 is really important here, because that's the period of this sine function. So that's about adding on a period. So it's really important that when you do that, dividing the whole solution by 3, you're also dividing that 2 pi n section as well. Okay, so let me just tidy that up. So we're going to get here x is pi on 12 plus 2 pi on 3n, or it is 3 pi on 12, which is pi on 4, plus 2 pi on 3n, where n is an integer. Okay, so n is an integer is important, and stating both sort of families of solutions if you'd like. Let's have a look at solving this equation with the cas. So if we solve this equation, menu 3(1), sine of 3x is equal to 1 on root 2, comma x, no domain, we'll get the general solution. Okay, so let's have a look. That looks a little bit different to ours. I'm just going to write underneath here, I'll rub it out in a second. So my cas is telling me that it's 8n plus 1 pi on 12, or 8n plus 3 pi all on 12. Okay, so that's not what our solution looks like, but it's different to our solution. We didn't write each family of solutions as one single fraction. So if we split this, let's break this up. This is 8n pi over 12 plus pi over 12, and this is 8n pi over 12 plus 3 pi over 12, sorry. Okay, so 8 and 12 have got common factor of 4, so that's 2 pi n on 3 plus pi on 12, and this is 2 pi n on 3 plus 3 pi on 12, which is pi on 4, which is exactly what we got by hand. Okay, so it doesn't matter how you write it, you could combine them together with the common denominator, you don't need to though. Our general solution is fine as we gave it previously. Okay, let's just erase that, let's have a look at this. Okay, find the general solution to cos of 2x minus pi on 3 equal to negative half, and hence find all of the solutions for x in the interval negative pi to pi. Okay, so this is one way you could go about solving trig equations. First find the general solution, and then use your general solution to find the specific solutions in a given domain that you're after. Okay, which is the way that some people would, whereas we've done it in reverse. We've looked at how do we find them in a specific domain, and now we're generalizing that. Okay, let's have a look at the equation. So the first part is done in that we already have cos on its own. Cos of 2x minus pi on 3 equals negative 1/2. Okay, so cos is negative 1/2. Let's think about our exact values. So cos is 1/2 when we're talking about pi on 3. Okay, and it is cos is negative, so our solutions are in the second and third quadrants. Okay, sorry, and I'm going to draw that vaguely straight. Alright, so here and here. Okay, so pi on 3 up from the x-axis in the second quadrant, and pi on 3 down from the x-axis in the third quadrant. Okay, so we want a general solution, so there's going to be two families of solutions. That the ones all located in the second quadrant, so 2 pi on 3 plus multiples of 2 pi, and the ones all located in the third quadrant, so that will be 4 pi on 3 plus multiples of 2 pi. Okay, so we also have quite a bit going on inside the cos function, so 2x minus pi on 3 is going to be equal to 2 pi on 3 plus multiples of 2 pi. Or the second family will be in the third quadrant, so 4 pi on 3 plus multiples of 2 pi. Now again, n has to be an integer. Okay, now again, we need to essentially solve a linear equation. I just want to have a look at this. Let's just again isolate one equation. So the first thing we're going to need to do here, because we're trying to get x on its own, is to add pi on 3, and then we'll divide by 2. Now we did division in the previous example, but if we add pi on 3 to both sides of the equation, I want to be really clear about the fact that when we add pi on 3, we're not adding to the whole side of the equation. We don't need to add it to 2 pi on 3 and add it to 2 pi on n. If we've done that, we've actually added it twice. So compared to if we were dividing the whole equation to both sides of an equation by something, we must divide everything. But if we're adding something to both sides of the equation, we don't add it to each term on each side of the equation, we just add it once to each side of the equation. And in this case, it makes sense to collect like terms together with the 2 pi on 3, because that fits nicely. Okay, so be really clear about the fact that you don't want to add pi on 3 twice to the right hand side, you just want to add pi on 3 once. Okay. So let's have a look at what we've got here. We're going to add pi on 3, so 2x is going to be equal to 2 pi on 3 plus pi on 3, so that's going to be pi plus multiples of 2 pi. And then 4 pi on 3 plus 1 pi on 3, that will be 5 pi on 3 plus multiples of 2 pi. N is an integer. And then we need to divide by 2, so again, like we did in the previous example, we're looking at the equation. If we want to divide the left-hand side by 2, we have to divide the entire right-hand side by 2, which means we get pi on 2 plus pi n. Okay. Alright, so we're going to have x equals pi on 2 plus pi times n, and we're going to have, that will be 5 pi on 6 when we divide it by 2, plus, dividing that by 2 as well, pi n. And again, the pi n is because the period of this graph is pi, and so once we find one solution, to find the next solution, we're adding on a period, a multiple of the period, or subtracting a multiple of the period. Okay, so n is an integer. Alright, so there's our general solution. So that's the first part of the question, find the general solution, and hence find all the solutions for x in the interval negative pi to pi. Okay, so specific solutions for negative pi to pi x is going to be. Okay, so I'm going to start perhaps in the middle and then we'll expand out either side. So when n equals 0, we've got pi on 2 and 5 pi on 6. Okay. Then when n equals 1, we'll have pi on 2 plus pi, which would be 3 pi on 2. Okay, so that's going to be out of the domain. In fact, if we add pi onto either of these solutions, we're clearly going to be getting a solution that's bigger than pi. So we're not interested in going past here. Okay, so these two solutions were here when n equals 0. So now let's have a think about going back the other way when n equals -1. So we've already worked out that if n equals 1, our solutions would be 3 pi on 2 and 11 pi on 6, which are both bigger than pi. Okay, so that's irrelevant. N is -1. It would be pi on 2 minus pi, which is negative pi on 2. That's in the domain. And it would be 5 pi on 6 minus pi, which is 5 pi on 6 minus 6 pi on 6. So that's minus pi on 6, which is also in the domain. If n were to equal -2, we'd be taking 2 pi away from both of these solutions, and so they're definitely going to be less than -pi. Okay, so there is our 4 solutions that are actually in the required domain. The other thing I just want to note quickly, if this question had just been to solve, let's forget about anything going on in there, if this question had just been to solve cos x equals -1/2, okay, if I was writing the general solution here, I wouldn't have written 2 separate solutions in the case of a cos equation, and that's because you always get symmetry about the positive x-axis. Okay, this is plus 2 pi on 3, and I could think about this as plus 4 pi on 3, or I could think about it as minus 2 pi on 3. And so it can be nice and efficient to instead write my solution as plus minus 2 pi on 3 plus multiples of 2 pi, where n is an integer, rather than write it as 2 separate families of solutions. In this instance, that wouldn't have helped me, because then when I added pi on 3 to both solutions, they no longer would have been the same plus minus, the same value, positive or negative. So that's why I chose to write them separately. And equally, again, I could have started here with -2 pi on 3 as this solution, and so then, you know, adding pi on 3, it would have become -1 pi on 3, and then this might be -pi on 6, okay, which is fine as well. So as long as you are able to represent the 2 families of solutions, doesn't matter where the start value is, it's the same family of solutions. Let's have a quick look at what this looks like when we solve it with our CAS. I suspect it would have used the -2 pi on 3 at the beginning, so we might get slightly different looking solution. So menu 3.1. Cos of 2x minus, pi on 3 is equal to, -1/2, and we're solving for x. Okay, so we get 6 pi n on 6, so that's pi n minus pi on 6, which would have been that would be the same as this one, okay? Or we get 2n pi on 2, so that's pi n again, but this time plus pi on 2, which is what we have here, okay? So the other family of this family of solutions that we've got as 5 pi on 6 could also have ended up being -pi on 6 plus multiples of pi n, which is the same set of solutions. That would have been what we'd ended up with if we'd started with plus and minus 2 pi on 3 at the start. Okay, but again, still perfectly correct. All right, last example here, I want to have a look at your textbook uses this notation on occasion, and I just want to interpret what this means for you. I wouldn't say that you need to be able to express your solutions in this way, but to be able to decipher what's happening here is important. Okay, so the general solution of an equation is x equals n pi plus -1 to the power of n inverse cos of 1/2, where n is an integer. Find the solutions in the interval -2 pi to 2 pi. Okay, so we've got our solution. X equals multiple of pi plus -1 to the power of n inverse cos of 1/2. Okay, so that's just your exact values. What angle gives cos of 1/2? Okay, so let's just think about that first. half our equilateral triangle. Cos will be a half if we're talking about pi on 3. So from the special triangle, we learn that cos of pi on 3 equals 1/2. So that automatically tells us that inverse cos of 1/2 is equal to pi on 3. Okay, so let's use that. So we've got x equals multiples of pi plus negative 1 to the power of n times pi on 3. Alright, so let's think what's going on here. So what we have here is if n is an even number, okay, if n is even, then this will be x equals n pi plus pi on 3, because negative 1 to the power of an even number will be positive 1. If n is odd, this solution is x equals n pi minus pi on 3, because negative 1 to the power of an odd number will be negative 1. Okay, so let's think about where those solutions are in the unit circle then. Okay, so, sorry, trying to draw a vaguely vertical line. Okay, so if n is even, the solutions will be n pi, so that's an even multiple of pi, which happens around here. Okay, so this is where we get even pi. That is, 0 is not technically even, but 2 pi, 4 pi, 6 pi, negative 2 pi, etc. Okay, and we want even multiples of pi plus pi on 3. Obviously, it does, in this case, it will also work for 0, even or 0. Okay, and that's because if n is 0, then we get 0 plus negative 1 to the power of 0 is positive 1, pi on 3. So if n is 0, then we still fit the first category, it'd be plus pi on 3. So even multiples of pi plus pi on 3, or odd multiples of pi minus pi on 3. Okay, so that will be the locations of our solutions. So therefore, they must have been solutions to a sine equation. Okay, so if you have an equation involving sine, it will be possible to use this notation to express your solutions. I'm not saying that you need to do that, it's unnecessary. Okay, so just in terms of interpreting what's happening here, so then if we want to find the solution, all the solutions in the interval negative 2 pi to 2 pi, we could just do that from our unit circle. Okay, so if we think about negative 2 pi, around to negative pi, around to 0, around to pi, and around to 2 pi, we're going to get our 4 solutions. So it is negative 2 pi plus pi on 3, so that is negative 5 pi on 3. Sorry, it's a 5. Negative pi minus pi on 3, so that is negative 4 pi on 3. Then 0 plus pi on 3, so pi on 3, or pi minus pi on 3, so 2 pi on 3. So that is all the solutions between negative 2 pi and 2 pi. But just being able to interpret that notation and work out what does that mean in terms of where are my solutions located in the unit circle. Okay, again, obtaining general solutions using CAS. Oh, sorry, there's some notation that's gone a bit awry there in the little box you've got written there, but essentially just what we were doing. So solving without adding a domain restriction will give you a general solution. Please don't write n1, n2, n3 in your answers on paper, just write n and make sure that you add that n must be an integer when you express the general solution.